So we're finishing out section 2.2 with a couple of examples to help us kind of get a sense of what's going on. So in this first example, we're given a system, and you'll notice right away that that system is autonomous because both of these differential equations do not contain anything having to do with the independent variable on the right-hand side. So both of these are a function, in this first case, f of x and y, and this one is some other function of x and y, but there's no t, so these are autonomous. This is an autonomous system. And that's good. Autonomous systems are where we're going to spend most of our time because non-autonomous systems get a little nasty. So the first thing it says is find the equilibrium points of the system, which means we got to set this thing up to solve two separate equations. We got to figure out where dx dt equals 0 and where dy dt equals 0. And so both of those are really just setting up pretty straightforward linear equations. And of course, we can do that, or we could have Maple do it for us. And so I'm just going to hop over and say, hey Maple, would you solve this system of equations? Now notice I put it inside the brackets to let it know that it's going to be a system of equations. And so I typed it in, and then we'll just hit enter and say, hey Maple, tell me what to expect. And my Maple is taking a little while to think about it. My processor must be really, really slow by comparison. And after what took to be entirely too much time, Maple spits out an answer. It gives us an x-coordinate and a y-coordinate. And so I'm going to scroll down here. So that's exactly where we would expect to find an equilibrium solution for this system. And so if we want to see what it looks like to get a sense of what's going on, we can produce a field plot. So before I do that, let me hop back over into the notes and say this thing has a solution at x equals -1/9 and y equals, the other one was 2/9, I think. Gosh, I hope so. And so that is the equilibrium solution. And so just I did that by using solve in Maple. And so just a little bit of interpretation here. This is saying at the location -1/9, 2/9 on the xy plane, we expect an equilibrium point. And just a reminder, an equilibrium point is where we expect there to be no motion. That means there shouldn't be any arrows there. And the arrows, as you get close to it, should be either headed towards it or away from it. And if you're looking at a field plot, they should be getting smaller and smaller and smaller. And so just to verify that, we'll hop over into Maple and take a look at what the field plot looks like. Now notice I did thick arrows, and I used the right-hand side of each one of the equations, just the right-hand side, and I didn't write them in terms of functions, right? They're just x and y. And this is what I came up with. And sure enough, as you get close to right around the origin, it just slightly to the left and slightly above the origin, somewhere in this area, we expect there to be a equilibrium point. And it makes sense based on what we've seen. So if we just want to see a phase plane with no indication of vector length, we can do that with a DE plot. And the DE plot, I think, is sometimes a little bit easier to read. And so, what do you know? It worked. It looks like we have somewhere in this neck of the woods an equilibrium point somewhere in there. And if we wanted to, we could add some particular solutions to that. Add some initial conditions. I added a whole bunch, including the actual equilibrium point right there. And so we can see what happens to those solution curves. It looks like no matter where you start on the phase plane, everything is taking you away from, heading out and away from that equilibrium point. And so if I wanted to plot this in 3D, because remember this plane has our time axis coming straight out of it, so we're only seeing a shadow of the actual curve. The actual curve is what we get with the plot with 3D. And what's really cool about this is as you rotate your 3D, and I don't know if Maple's going to give me a hard time with this, but as you rotate your 3D graph, you notice that there's that one quote-unquote curve straight down the middle that's actually just a straight line. And what you're seeing with that is only movement in the time direction. There's no X and there's no Y motion. And that corresponds to the initial condition that's exactly at our equilibrium point, right? All these solution curves are kind of spiraling out and away from that equilibrium point. And by the way, I make them kind of head back towards the equilibrium point in time by changing from t equals 0 to t equals -1. So I kind of play the curves backwards in time as well. But the one thing that's not curving and not moving at all is when your initial condition is exactly equal to the equilibrium point on the graph. So all the other initial conditions produce curves that appear to be flying away from the equilibrium point as time goes by. So that's it for this example. So let's kind of wrap up and finish up what we had here. So that was part A. Part B says sketch the direction field. That's using field plot. Oops, let me scoot this up so you can see. Field plot in Maple. We're not going to do this by hand. Ugh. Right? And we also sketched a phase portrait. And that gives, this one will give the direction field, or better yet, the vector field. And if you use DE plot with initial conditions, you can get the phase portrait. If there's no initial conditions, then that's just, we call it just the phase plane, right? So you got to have some initial conditions in order to get the phase portrait. And then part C, we can do that again. That's about describing the behavior of the typical solutions. And so for this one, we saw on the screen, on the Maple screen, that all solution curves spiral away from the equilibrium point. And they do it in a counterclockwise I like to abbreviate CCW for counterclockwise or CW for clockwise in a counterclockwise direction as t gets bigger and bigger and bigger. So as t goes by, as time goes by, they spiral away from the equilibrium point in a counterclockwise direction. I suppose I should say in a counterclockwise direction. Right? So there's one more example in the top of that last page in the notes. Says we've been lucky so far. We've been lucky so far since all of our equations have been autonomous. That is, no independent variable on the right-hand side. And that sort of lets us ignore the t values in all our work. But in later chapters, that's not always going to be the case. We're not always going to be so lucky. But for right now, we're going to take it and run with it. So here's another slightly more complicated system. Now this one is a little bit more complicated in terms of finding the equilibrium points, but we can still use the same process that we did before. And if you remember, the process was to take a look at each one of our differential equations, set them equal to 0. So where are we going to find the equilibrium locations? Well, dx dt equals 0 when x squared minus 4 equals 0. And that's going to happen when x is plus or minus 2. And dy dt is equal to 0 when 1 minus y is equal to 0. And that only happens when y is equal to 1. So here's an interesting situation. We have two values for x that make dx dt equal to 0, and only one value for y that makes dy dt equal 0. So what do we do? Well, the answer is we got to use both of these, and that means they must correspond to the same y coordinate. And so that means 2, 1, and -2, comma 1 are both equilibrium points, right? Equilibrium solutions or equilibrium points on the phase plane. And so in order to make sense of what the heck they are, we can do a quick maple graph or maple plot. And so this is a DE plot with some initial conditions to get a sense of what's going on. And sure enough, if you look for 2, comma 1, the scale's a little tough to read, but if this is 4, then 2 is about halfway, and 1 is going to be right about, hey, what do you know, right about there. That's one of our equilibrium solutions. And the other one happens at -2, comma 1, which is right about there. And sure enough, there's some interesting things happening with the solution curves there. And you can spot what's happening at this place. It seems like everything is headed sort of like it's headed towards it, but then it runs away from it at the end. And so it's headed towards in this direction, but away in the other direction. And there's a fancy name for that. And we're going to get more into these later, but this is what's technically called a saddle, because it's headed towards, but also away in the two directions. And the other equilibrium point, this guy right here, you can tell everything is headed zoom, 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 zoom. Everything is headed towards it. And so that's a little bit more obvious that it's a sink. And so our old pals sink and source are there, but now we don't call them nodes anymore. We're going to refer to them as saddle points. It's a little bit more interesting. You might have seen that in Calc 3 before. So we can do this in Maple, and I've got the code for this down below on Maple with my initial conditions. And so you can verify what we had on the notes, on the actual document of the notes. And sure enough, if you were to type in the actual locations of our equilibrium solutions, they wouldn't show up here. The only way you get a visualization of a curve is if there's motion, right? And so if you were to type in an initial condition of 2, comma 1 or -2, comma 1, they actually wouldn't show up here at all. But they would show up when you did a DE plot in 3D, because then you'd be seeing it as it's moving out of the screen, now literally out towards you from the screen. You can't see that because it doesn't cast a shadow on the phase plane, but you can see it when you look at the DE plot. So that gets us to the end of this section, and you'll note down at the bottom it says strongly recommended. Strongly recommended. There's a couple of exercises that you should really turn your eyes to in the book from section 2.2, exercises 21 and 23. You should check those out. We also have some classwork that we're going to do together during our session time, but these exercises are handy for you to get a little bit comfortable with. So that gets us to the end of 2.2.